The swinging bridge at Sluiskil over the canal from Ghent to Terneuzen forms a bottleneck for road traffic. The bridge is open an average of 5 hours a day due to intensive shipping. This leads to long waiting times. Since the opening of the Westerschelde tunnel, the traffic has even increased. In 2020, every day over 20,000 vehicles will use the bridge, and costs of waiting times will run up to 10 million euros a year and hinder the economic growth of the canal district. But there is a solution, a tunnel. The Sluiskil tunnel. Of course, you have to have a certain capability. Drilling a hole of more than a kilometer with a diameter of over 11 meters is one of them, deep underground, under the canal from Ghent to Terneuzen. Is it even possible? Yes, it is. It has previously been demonstrated by the construction of the Westerschelde tunnel. You do have to have a drill that is adapted to the geological conditions beneath the canal. In actual fact, there will be 2 tunnels. Each tunnel is 1150 meters long and provides space for a 2-lane road. At its deepest point, the tunnel runs roughly 35 meters below the surface. At that depth, the working pressure is 3.5 times higher than that of the open air. The drill we are going to use for this is the Herrenknecht TBM. In reality, it's a whole factory. It consists of a cutter head followed by a series of gantries. The cutter head itself consists of a cutting wheel on the front with a diameter of almost 11.5 meters and an excavation and working chamber. Behind the cutter head there is an area for installing concrete rings. Then follow the gantries with a control cabin and all the electrical and hydraulic installations. The entire drill is roughly 80 meters in length and is adapted to the properties of the Zeeland's clay and sand. The cutting wheel is driven by electric motors. There are also 2 airlocks for inspections and maintenance. Hydraulic cylinder presses enable the drill to move forward. The cylinders brace themselves against the last previously installed concrete segments, thereby pushing the drill forwards. The drill works in 2 phases. The first phase is the installation of a concrete lining ring. The parts of this, known as segments, are supplied by the segment feeder and subsequently lifted by an erector. This places them within the steel mantle of the tunnel boring machine with extreme precision so that they align precisely with the previously installed concrete lining ring. When the concrete segment is installed, the hydraulic cylinders are temporarily retracted to create enough space for the new segment. The 7 segments are positioned with millimeter precision, secured and bolted in place. The last segment, the so-called keystone, is conical in shape and is inserted from the front. The segments are transported from the second gantry to the erector. But first, they are transported from the surface down the previously excavated section of tunnel to the second gantry by special vehicles. This gantry also houses the control systems and operating systems. Amongst others, there is enough space for a grout mortar container and the electrical and hydraulic systems. And there are provisions for the supply of bentonite and the removal of slurry. Phase 2 involves boring. But how does that work? Behind the cutting wheel is the excavation chamber. This is separated from the working chamber by a diving wall. The 2 chambers are connected in the form of communicating pipes. The chambers are filled with bentonite. Increasing the pressure in the chambers to just over that of the soil pressure creates a stable bore front and allows the drill to do its work. Bentonite, also known as swelling clay, is a naturally occurring type of clay consisting of particles that are so small that they form a type of gel when mixed with water. This gel is very suitable for maintaining the stability of holes in the soil. It is named after the location where it was first discovered, Fort Benton in Wyoming. The excavated material falls into the excavation chamber. Sand and clay dissolve in the bentonite, while more coarse pieces sink to the bottom. 2 agitators guarantee the smooth removal of these pieces. The excavated material is pumped through the suction line to the separation plant at the surface. Here, the soil material is separated out and removed from the bentonite suspension. The clean suspension is transferred back to the excavation chamber for reuse. Together, the two tunnels, each 1150 meters, are 2300 meters in length. For this, 1150 rings of concrete segments are installed. Each ring consists of 7 segments and a keystone. So 9200 parts in total. 230,000 cubic meters of sand and clay are excavated and removed. With an average speed of 10 meters per natural day, the drill can complete 1 tunnel pipe in 3 months. With an interval of 3 months between the excavations of the 2 tunnels, this means a total drilling time of roughly 9 months. For an amount of 300 million euros, over 20,000 vehicles per day will make use of the tunnel as of 2015. This means savings of 10 million euros in waiting time costs and also the availability of 10 million euros for economic expansion. Experience with drilling the Westerschelde tunnel has led to many new technological developments that can now be used. Not only is this extremely useful for drilling the Sluiskil tunnel, but it has also been of groundbreaking significance for drilling continually longer tunnels with larger dimensions.